Next Curve.
Welcome to another episode of neXt's Rethink podcast, where technology industry thought leaders discuss the trends and technologies that are shaping our digital future. And I'm Leonard Lee, Managing Director and founder of neXt, and I'm joined by Dee Freeman, Research Fellow. And today, we're very happy to have a very special guest, Jim Walker, a former Gartner colleague of ours and CEO of WLP Concepts. Jim worked with Dean on the semiconductor team at Gartner, and he specialized in semiconductor packaging. Welcome, Jim. Really glad to have you.
Thank you. I'm looking forward to our discussion today.
So do you want to take a moment to share your background and some of the research focus at WLP Concepts?
Thank you, Leonard. WLP Concepts stands for World Level Packaging. It's kind of the wafer level packaging. Kind of the mantra in today's world of where the technology is going. That heterogeneous integration are kind of the buzzwords that have been for a little while, but we continue to get more wafer-like in the packaging and assembly area. As you mentioned, I spent a lot of time at Gartner looking into the packaging and marketplace, doing a lot of research in that area, and spent time focusing on the OSAT, or the outsourced semiconductor and assembly test services market, which is basically the companies that provide that packaging, assembly, and test service on an outsourcing basis to all of the IDMs and OEMs. And that market basically over the past 5 years especially. We can talk further, but the Chinese obviously have entered that market in a very big way in the past 10 years. And especially past 5 years.
Okay, great. Gentlemen, today we're going to talk about heterogeneous computing, and some in our viewership might not know what that is. So we'll cover the following discussion points. So the first thing we'll talk about is, well, what is heterogeneous computing and what is heterogeneous packaging? And then we'll talk about what are the key design trends and technologies driving heterogeneous computing. And then we will cap things off with a little bit of a discussion on the implications on the semiconductor industry that this thing that we call heterogeneous computing we will have. So,
well, why don't I start there, and then Jim can pile on in a minute. What has happened is we started to build computers is getting to the point where you can't put enough cores on one chip in order to get the compute power that you need. You also have issues with the memory structure because you have to have the memory close to the logic to keep things from overheating and also to make things faster. So what companies have started to do is they've started to take cores and putting them together on a type of package that enables them to essentially put a mini server on a small PCB board. And that is finding its way into both the server area, artificial intelligence, as you and I have talked about in the past, Leonard. Now you're putting on the CPU, the GPU, the accelerator, and special memories in order to try to get that device to work faster or to get the so-called neuromorphic compute. So that's basic nutshell what I believe heterogeneous compute is taking those cores, putting them on a substrate or in a package, and then allowing that to give you much more power or to perform actually better than you would if you were trying to do this on a single chip.
So, Jim, what's the role of packaging in heterogeneous computing?
It's very interesting what has happened. For the longest period of time, we were integrating more and more functions on a chip, and packaging was kind of behind the times where we had to, in essence, make the chip slow down, and the package was bigger than the chip for a long period of time. And you'd have too long a path length for the signal to travel from one chip to another. But that was the way it was. It went into the PC board and came back up into the next chip and what have you. And we've done that for years and years, and that's why you have the PC board to carry all these individual chips. Well, more and more we got into, over the years, taking all of those various chips and putting them together on one big chip, okay, and integrating memory and integrating the various functions, input-output functions, which might have been separate 20, 30 years ago, or now on the, all on the chip. And in that, we kept on putting more chips together on one piece of silicon. And what that did is we got to the point where it takes too long to design that piece of silicon, okay, to put all those transistors on one chip. It's very costly. You have a high volume application because taking the time and doing that integration on a chip is time and expense. There's a huge non-recurring expense charge from a design standpoint. So you either got to have a high volume to do that. In essence, continue on Moore's law, okay, to keep on integrating on chip, because that's basically what Moore's law is. We got to a point where it's taking too long, it's too costly, so we're kind of disintegrating, if you will. We're taking some of the functions back off of this very large chip and putting them onto a carrier substrate, trying to make the carrier substrate as fast as possible from an electronic circuit standpoint to carry the signals, and power and ground for that matter. What you've got, in essence, is we now are disintegrating instead of integrating. And what that allows us to do, in essence, is you call it a heterogeneous integration, because we are integrating a substrate now instead of a chip, okay? Or we're integrating at the package level instead of the chip level. And the package level, by putting these chips on top of each other, okay, instead of side by side with through silicon vias or via arrangements, we have a shorter distance than horizontally and side by side. So you're seeing this chip stacking, or you're seeing a combination of both, side by side and chip stacking. In essence, it appears like one big chip. Okay, you then take that and put it onto the system board. It functions like one big chip, looks like one big chip because we did plaster or put it in a ceramic package or material we want to use. But in essence, it's a variety of chip which we can even take off the shelf and arrange and put them together, so the design cost is less, the time to market is less, but it isn't as optimum, obviously, as putting everything on one chip, okay? Path lengths and the feature sizes, things like that at a package level are much larger than they are on the integration of 5 nanometers on a chip level. But that's what we're doing, okay? Because it gives us the flexibility to cut and paste, if you will, in essence, via packaging. And that's where we're headed. And of course, there's various approaches to do it. There's various materials to do with and various carriers. I mean, we've got glass carriers now. We've got silicon wafer carriers. We've still got plastic carriers, like PC boards with different materials, whether they're epoxy or polyimide or what have you. That's where we're going, is this disintegration to meet market needs, time to market. Huge.
Does that have any implications on how we're seeing computing devices evolve? We hear a lot of the big semiconductor names out there talking more and more about heterogeneous computing, and I guess I'm really curious what you gentlemen think is the reason. Why is heterogeneous computing so interesting, or at least from a marketing perspective, something that they've seemed to be latching onto and developing as part of the narrative for their brands?
Yeah, so from my perspective, one of the reasons you're seeing heterogeneous compute, it may have started before Lisa Su mentioned it at IDM a few years back. You got to the point where you couldn't put enough cores on a chip to get the power that you needed. The AMD philosophy was, all right, let's break this up. You can still now have 34 cores, but now I've got 4 chips for those 34 cores. Yeah, she said it's a little bit slower because of the interconnect, but I'm more powerful, overall. The other thing that you can start to do with heterogeneous compute is you can start to stack memory on top of that logic, and it actually operates faster potentially than if that memory is on chip due to the interconnect delay. Also creates less heat because you don't have as much resistance, because you can have larger wires. You're going through silicon vias to the memory versus a lot of tiny wires heading over there. So that's sort of the basic premise. But the other thing it allows you to do, and Jim touched on this in his earlier comments, is with the disintegration. In the old days, what you did is to have a server that had GPU as well as the neural network or the neuromorphic compute. I'd have 3 different chips on a PCB board, and it would take time for the electrons to travel or the information to travel between those different chips. Now with heterogeneous compute, I can cram those much closer together. And so I can have a MPU, I can have a neural network chip, I can have a graphics interface chip, I can have an accelerator, all on the same board, very close to one another, which allows me to build much more powerful systems for things like artificial intelligence that I was not able to do in the past. So I think you're seeing Intel jump on this big time. We're seeing NVIDIA try to get into it with things that they're doing. AMD is a leader in the space. IBM supports this in many different ways. Samsung you don't hear so much about, but I believe they are very much on board with this as well with some of the work that they're doing. And so I think you're going to continue to see it snowball as we move forward and as artificial intelligence becomes a much larger part of our lives.
And ARM as well, right? TechCon, they were talking about heterogeneous compute all the time.
ARM does the design and the cores. They don't actually build the chips, so they provide some of the intellectual property to help make this happen.
I think that the key of why we're seeing this artificial intelligence and why from a production manufacturing standpoint is the flexibility of where we're going. This heterogeneous computing, therefore heterogeneous packaging. The flexibility is necessary. The volumes are going to be very, very customized, medium to low volume, very customized type of volumes. And with that, you really can't keep on integrating, as I mentioned before, on a chip because of the time to market and the design costs and things like that. And of course, pushing the limits down at 5 nanometers, there's only 2 or 3 people can do that. It's very expensive. And so you want to get as much cost out of the product as possible. So you want the flexibility in order to get that cost out. And we're seeing more and more of that with the packaging arena of taking more items, if you will, that have been there for a while off the shelf and trying to put them together now. The rearrangement of those items, whether they're stacked side by side, and the material set with regards to the interconnect substrate, those have to be selected too, as each one of those gives different characteristics. Some are very good thermally, some are not. Some are very good electrically. The others might not be as good electrically. So you've got to pick and choose, and you're sort of sub-optimizing, if you will, because again, the optimization, if cost was not a factor, if you will, and time to market was not a factor, and product life cycle was not a factor, you'd go with integrating on a chip forever, I think, if you could do it. But we are getting to a point where we're going to have to disintegrate, and we've been seeing that over the past years more and more, even as with the wafer level packaging, where the package is basically the same size as the die. Still at a point where you've got to take the functions that Ian described and put them in separate areas so that you can rearrange things to optimize your system.
So which device market segment is driving this? Is it servers? Is it smartphones? Is it the PC? I mean, what are the devices that are really pushing the envelope of heterogeneous computing and the demand for it?
Well, I think the cloud is a major factor in artificial intelligence. Those areas are what's kind of driving the leading edge from a computing standpoint. From a heterogeneous packaging standpoint, high volume tends to drive the technology. And so you're looking at cell phones and that type of communication marketplace. The computer does drive some of the interconnect technology, but in order to minimize cost, you got to have a high volume driver, and we're able to do that with heterogeneous integration more and more, and wafer level packaging more and more with the cell phone.
For some of the folks who are in our audience who are less familiar or knowledgeable about the semiconductor industry, I guess a good example is something that we might want to surface up, but I'll throw one out there. I always think of the smartphone chips as being a good example of heterogeneous computing as well as packaging. If you look at the device, there's a lot of things going on just to drive the density of those devices. Would you gentlemen think that's sort of a fair example or something that's digestible for our audience, or would you beg to differ?
I'm not sure if the smartphone is a great example because you're not building the number of cores that you need. The smartphone still it's not quite integrated all on the same chip, but it's pretty close. You may have some, I'll call it system and package type things in that. Where you're seeing the heterogeneous compute is where you need large cores and a lot of compute power. So PCs would be a lower end application for it, but as Jim mentioned, servers, artificial intelligence applications, something where you're looking at multiple cores, you're looking at a GPU in there, you're looking at an accelerator in there, and you're looking at high bandwidth memory on board. And you just don't have all of that packaged into a cell phone yet. Jim, would you agree or?
I would agree. You don't have a lot of that packaging in a cell phone. What it does is it filters down as we get the cost down. It really depends on what the future function, if you will, of the cell phone is and how many more functions or how many more features, benefits we want to put on them. I mean, we've got medical sensors that now attach to cell phones. So the factor of using your cell phone in a more artificial, intelligent manner. I mean, what we've really got is you got a desktop computer and even that, servers and things like that. Everything has got computing power. Mm-hmm. And so do you want to make it, as fast as possible, but it's not portable? Or do you want to have the portability, but it's not as fast as possible? Or, how do you make the all-in-one? Because that's really what everybody likes all the time, is the all-in-one approach to whatever you're going to do.
Right.
And so eventually, artificial intelligence will filter down into a cell phone as well, more and more.
Hasn't it already done that? I mean, if you do look at, let's say, for instance, Apple Silicon chip that was announced at the last Worldwide Developer Conference, that chip design incorporated a lot of different types of computing devices or computing elements. I mean, it has a GPU, it has an image processing unit, it has NPU.
But it's how they're packaging it, Leonard. It's got a lot of power. It's got a lot of stuff in there, but they're not throwing it all into the same small package like you would for a heterogeneous compute. It's still a little bit piecemeal. You have a little bit, you could call it heterogeneous packaging, but you wouldn't call it heterogeneous compute.
Okay.
Right.
We call it a system and package because you're taking different aspects and putting them in the same package. So that's where the mix-up comes. And, to be truthful, when I have conversations with people in the industry, you've got to be careful because there's heterogeneous packaging, there's heterogeneous compute, and they're two different animals. The heterogeneous packaging plays into heterogeneous compute, but then you've got the heterogeneous packaging. And Jim's been preaching this for years about system and package, how we need to go in that direction. And, a lot of the OSATs have a very strong SIP business out there right now. But that's different than what we're looking at from a heterogeneous compute perspective.
Those are good clarifications. So why don't we move on to our last topic here, which is what we think the impact or implications of heterogeneous computing as it continues to evolve on the semiconductor industry.
As you mentioned, and rightfully so, Dean, that heterogeneous computing and heterogeneous packaging are two different things. From a heterogeneous standpoint, I think we're further along in the packaging realm. We're splitting things up than we are in the computing realm, okay? We've been focused so long on putting everything together in the computing realm that taking it apart is a little more of a challenge, if you will, than from a packaging standpoint. And part of that, you mentioned SIP or system and package. Basically, what packaging companies have been doing for a long time is stealing some of the marketplace away from the board level and system level manufacturers, okay, by integrating at a package level. And as we've been talking about, putting a lot of components onto a miniature substrate, which is like the old PC board that was system level, and putting them together and then making them look like one chip and one package in the final system. When it's almost like a bunch of daughter boards connected to a motherboard, and all you have left is a motherboard with a bunch of packages on it, which are all daughter boards, because the package used to be, is the former daughter board. That's kind of what we're doing there. But I really do believe that the future is going to be limited even at the package level in certain aspects, because we haven't really talked about thermal issues. One of the challenges in going to put multiple die on a substrate, whether it's a board and system or whether it's a package, okay, is the distribution of heat and how those electrons flow and which electrons are moving, and which ones are not turned on at the moment, and the heat up and the cool down of all of those electrons going all over the place. You have to balance the thermal with the electrical, okay? Because if you have too much hot spots, you will have reliability problems, you have warpage, you have a lot of problems, okay? And if that isn't balanced from a design standpoint, and therefore that even further relates to, disintegration of the heterogeneous computing approach, where you're taking it apart, you got to make sure when you take it apart that everything is balanced.
Mm-hmm.
Yep.
Because battery power is key in a portable device, but the thermal issue, as we get smaller and smaller and put more stuff in a system, becomes bigger and bigger. And that is going to be a challenge in the future.
Jim mentioned with both heterogeneous packaging and heterogeneous compute, thermal is a huge issue that has to be figured out. Right now, they're just predominantly putting several cores or MPUs on the same board. In some cases, stacking high bandwidth memory with that to make sure you've got the memory access. And that's the extent of heterogeneous compute. As we expand more into neuromorphic compute and things for artificial intelligence, you're going to have to be stacking a lot more compute power in a small area, and getting the heat out is critical. But I think what this is going to do for the industry, it's really going to be a new renaissance for the packaging industry. They are trying to slowly start to position themselves into the heterogeneous packaging space. Unfortunately, it's very expensive for them because most of this now uses front-end equipment versus the traditional back-end equipment that we've seen. So they have to go out and buy some headers that can create through silicon vias. They have to buy the electrochemical plating tools that are a little higher price than what they've been able to use previously with their tank electroplating. The potential for the OSATs to really get some significant growth in the industry as we go on. There's also the possibility that the IDMs, AMD, Intel, and TSMC will try to keep this in-house because it is a pretty high margin product. And so it will enable them to sell things at a much higher value. And then the last thing that we've got to get going on this is standards, because you really don't have a good standard. I can't take an AMD core and put it next to an Intel core, or I can't take an AMD graphics chip and put it necessarily on an Intel board. NVIDIA is Switzerland at the moment, because I see that both with AMD chips as well as Intel chips.
Mm-hmm.
But you have to get to the point where there's standards that allow you to plug and play so we can get to that really heterogeneous packaging that Jim was talking about earlier.
So, gentlemen, thanks for a great discussion, and I think it's going to be very informative and enlightening for our audience. And Jim, I just want to give an opportunity for you to let our audience know how they can reach out to you and get access to some of your research.
They can email me at MaseratiJim@gmail.com. And that's Maserati like the car. And so the question becomes, did I have one? And the answer was, I did have one until my son blew it up. So that was many years ago. It's too many years ago, 20 years ago. But it was a fun car.
Yeah, I'm sure. Sounds like it was.
Yeah,
at least for your son.
That was for both of us until that happened. Anyway,
So yeah,
I adopted the Maserati and put my name after it. And it was a lot of fun.
Okay, well, to our audience, Jim is a great resource for those strategy and product management folks in the electronics and tech industry who want to know the technology and market trends that will impact your product roadmap. So please reach out to him. He's a very friendly guy and very knowledgeable. Jim, Dean, like I said, thank you so much for today's conversation. Appreciate both of you sharing your experience and insights. And thanks to our viewers and listeners for tuning in. And I hope you join us next time for another episode of Rethink. And remember, please subscribe to our YouTube channel, our Apple Podcasts, and our research blog at www.next-curve.com. Jim, hopefully we'll have you on again sometime soon. It was
My pleasure.
really fun. And it's really great to see you. And I know that Dean missed you a lot, so.
Oh, yes.
I miss Dean too. We need to get together and water ski, Dean.
Yeah.
You betcha.
Like it.
A couple of old guys trying to get up on the list.
Yeah.
Okay, well, be healthy and stay safe.
All right, thanks.
Thanks, Leonard.
Visit us at www.next-curve.com.